Hello everybody and welcome back. Let's get some learn on. Okay, so you can see do now, quick review 8.1 on top of page 441. It's under the light blue banner, so pause the video, go do that, and then come back. I'll pause while you go do that. And here you have some answers. It looked like that do now was just like evaluate functions, and then at the end they threw in some limits, so check your answers there. Still drinking coffee. Next thing on our flip chart, we would have had a free response question as our assessment for that last unit, but hey, we didn't really do that. So we are going back to section 8.1, sequences. Sequences, you may remember we skipped this section when we were in chapter 8, but it really does line up with series. And although sequences won't be on the AP test, they never really are, it is a definite thing that you need to know about in order to be able to understand what a series is. So a sequence, the big picture here, sequences are just lists of numbers in order. So defining a sequence. A sequence is a list of numbers written in an explicit order. Explicit here does not mean, cursing. It means a very decided number. It is set right there. For example, a sub n, the sequence of a sub n equals a sub 1, a sub 2, a sub 3, blah, 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 until the sequence ends. Where a sub 1 is the first term and a sub n is the nth term of the sequence. If you let a sub 1, a sub 2, a sub 3, blah, blah, blah be a function with domain the set of positive integers and range a1, a2, a3, etc., etc., etc. If the domain is finite, then the sequence is a finite sequence. If the domain is infinite, then the sequence is an infinite sequence. All that means is if you can count the number of numbers that are in a sequence, it is finite. If you cannot count how many numbers are in this sequence, it is infinite. If that's confusing, it will become more clear as this lesson goes on. So pause if you need to see this, and yeah. Alright, flipping over here. Find the first four terms and the 100th term of the sequence a sub n, where a sub n is equal to -1 to the nth over n plus 2. And yeah, that should show up on your screens, I believe. I don't know if you guys can hear the street cleaner is apparently still going on. I guess that's an essential service. So find the first four terms and the 100th term of the sequence. Okay, so first four terms are just going to be a sub 1, a sub 2, a sub 3, and a sub 4. Alright? So what that means for a sub 1, notice how in a sub 1, n is equal to 1. That just means we've got -1 to the first power over 1 plus 2. Essentially what we're doing is, imagine this is f of n. We're plugging in the number there. Down here, we've got -1 to the 2th over 2 plus 2. Notice how all I did was change the n to the subscript here. -1 to the 3rd over 3 plus 2. And -1 to the 4th over 4 plus 2. And of course we would want to simplify these things, like -1 to the 1st is -1, so this becomes -1/3. -1 squared is +1, so we have 1/4. And -1 to the 3rd, lost my train of thought there, is -1, so -1/5 is what we have here, and -1 to the 4th would be +1/6. So this introduces our first idea of an alternating sequence. Alternating because the signs alternate between positive and negative. You can actually say now that a sub n is going to be equal to the collection of the numbers. That's supposed to be one of those face bracket thingies. -1/3, 1/4, -1/5, 1/6. As it's written right here, this is a finite sequence. If we went on forever and ever, it would become an infinite sequence. So now looking a little bit further, we didn't actually do the 100th term, so we would actually have to do a sub 100, which would be negative 1 to the 100th power. That sounds hard, over 100 plus 2. And since 100 is even, this will be positive 1/102 right there. So hopefully not overly difficult to figure out there. Explicit definition. So the explicit definition of a, actually here, let's say this is 1/102th, and let's just imply that it is an infinite sequence. So it goes on forever and ever, and if you want to write out the nth term, you can actually just take this expression and put it as the nth term. But I ran out of space over here, so I'm not going to do that. An explicit definition means the formula is in terms of n. Make better sense when compared to... Okay, so yeah, it means the formula is in terms of n. So you might be looking at this and like, how the heck does it not be in terms of n? I'll show you that in a little bit, but this is an explicit definition of a sequence. All right, cool? Right, let's move on forward. Find the first 3 terms and the 7th term for the sequence defined recursively by the conditions. B1 equals 4, b sub n equals b sub n minus 1 minus 2 for all n greater than or equal to 2. So as the directions imply, this is the recursive way of defining a sequence, and recursive just means you're given the first term and you're told how to find the terms after that. Yeah. All right. So here, I want to find the first 3 terms. So b sub 1, b sub 2, and b sub 3. I also want to find b sub 7. All right. So b sub 1, hardest one to find. It's right there. It's 4. B sub 2, I can look over here, would now actually be b sub 2 minus 1 minus 2. Well, 2 minus 1 is 1. This becomes b sub 1 minus 2. I have to look back previously, find out that b sub 1 is 4. I get 4 minus 2. So basically, all this is saying is take the previous number and subtract 2. So to have b sub 3 would be equal to the one term before 3 is 2. Oh, let's actually write it down. 2. So I'd have 2 minus 2. 2 minus 2 is 0. And to get b sub 7, oh crap. I need to know what b sub 6 is. It's b sub 6 minus 2. So I go back and I find b sub 6. Well, b sub 6 is b sub 5 minus 2. To find b sub 6, I need to find b sub 5. b sub 5 is b sub 4 minus 2. To find, I hope you guys can get the picture at this point. I now need to find b sub 3. Whoops. Hard to say one number and write a different number there. So here I can actually see this is negative 2. This is negative 4, negative 6, and negative 8. I can now find b sub 7 is negative 8. So now I can say b sub n, that sequence, is equal to 4, 2, 0, negative 8. Now the bad thing is, in order to write out the nth term, like I said on that last problem, we would actually have to rewrite this explicitly in order to be able to write out the nth term. Because with recursive definitions, you actually can't just determine what the nth term is. You need to know what the terms are before that. So yeah, there's that recursive. And here's a little bit better of a recursive definition. Formula depends on the previous term in the sequence. Ooh. We're going to take a pause here, and I'm going to give you a really famous sequence. This really famous sequence is called the... Whoops. spell his name, Fibonacci sequence. And if you can't pick up the Fibonacci sequence just by looking at it, I think I've told you guys some jokes involving the Fibonacci sequence before, but also, I'll tell you how it is. So f sub n is equal to 1, 1, 2, 3, 5, 8, 13, 20, 1, blah, 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 blah. Alright. So if you want to try to figure that sequence out, it's actually pretty cool. The only two numbers that are defined in the Fibonacci sequence are f1 and f2. They're both defined as 1. F sub n would be equal to f sub n minus 1 plus f sub n minus 2 for all n greater than or equal to 3. So digest that for a second. In order to get a term in the Fibonacci sequence, you add the two numbers previous to that. So, first two numbers explicitly defined, add them together, you get 2. To get this number, add the two previous numbers. 1 and 2 gives you 3. 2 and 5, or sorry, 2 and 3 gives you 5. 3 and 5 gives you 8. 5 and 8 gives you 13. 8 and 13, you saw me stumble there because arithmetic, 21. So now for the incredible joke time. They had the Fibonacci conference this year. I hear it was as good as the last two combined. Hey yo! All right, cool. Nice little pause for the joke. All right, so that last sequence that we had, sequence B, is actually called an arithmetic sequence. An arithmetic sequence. And a sequence A sub n is an arithmetic sequence if it can be written in the form A plus D, A plus 2D, A plus n minus 1 D for some constant D. The number D is the common difference. Each term in an arithmetic sequence can be obtained recursively from its preceding term by adding D. A sub n is equal to A sub n minus 1 plus D for all n greater than or equal to 2. So if you need some time to write that down, pause it. I'm going to do some explaining here. So arithmetic sequence just means for each term, you add on a number. And that number is called common difference. So we can actually look back here in this in this sense, in this sequence right here. We start with our number, and then we're adding -2 for each new term here. So in order to get the explicit definition on this, I know that the nth term is just going to be repeated addition onto that number 4. So to find B sub n explicitly, I can just talk about repeated addition, and repeated addition is itself multiplication. So B sub n is going to be 4 plus the number that I'm repeatedly adding on to here, or repeatedly adding on to the terms, is -2. And the number of times that I've added that on is actually, well, at 2, I've added it on once. At 3, I've added it on twice. At 4, I've added it on thrice. That's actually that n minus 1. That's this formula right here. That's an important formula. You guys might not have noticed that that was a formula in there, but really that formula is just A sub n is equal to A plus that n minus 1 times D, which you can see we actually have right here. And I'd like to clean these up a little bit. So 4 minus 2n plus 2, so it'd actually be 6 minus 2n would be the explicit definition that I would use on there. But this only works when you're talking about arithmetic sequences. There are other types of sequences, like that Fibonacci sequence is not arithmetic. That's actually really hard to write out explicitly. Alright, cool. So, arithmetic sequence. Given the arithmetic sequence, -3, 1, 5, 9, find A, the common difference, B, the ninth term, C, a recursive rule for the nth term, and D, an explicit rule for the nth term. Okay, so a couple things here. A lot of stuff going on. A, in order to find the common difference, you just take two of the numbers and find the difference between them. I mean, they should be the same distance apart, whether you do 1 minus -3, 5 minus 1, 9 minus 5, or you could even do this. D equals 9 minus 1 divided by 2 for those two steps there. Here, I would have actually added on the common difference twice. So this becomes 8 over 2, which is 4. You could get from any of these. I mean, 5 minus 1, 9 minus 5, 9 minus -3 divided by 1, 2, 3. 12 divided by 3 still gives me 4. B, I want to find, let's just call this sequence A sub n. I want to find A sub 9. Alright? In order to find that one, well, we know we've got the fourth term here. We can find the fifth term is 13. 13, 17, 21, 25, 29, right? So A sub 9 is going to be equal to 29, which really, there, I'm just using the recursive rule of A is equal to -3. A sub n is equal to A sub n minus 1 plus 4 for n greater than or equal to 2. So that's what I was doing for that, for finding that ninth term there. Now for part D, I know that in order to find the nth term, I'm taking that initial condition, A sub n, and taking that initial term, -3, adding on to it 4, and the number of times that I'm adding 4 on is whatever step I'm at, minus 1. So n minus 1. Which again, I like cleaning these up a little bit. -3 plus 4n minus 4. So -7 plus 4n. Just to be clear, you do not need to have this. You could leave it here. And also, to be clear, I could find A sub 9 really easily using this formula. -3 plus 4 times 9 minus 1. Well, 9 minus 1, that's 8. 8 times 4 is 32. Minus 3 gives me 29. It's just a little bit easier when I use the explicit definition. Isn't that cool? Yeah, I think so. All right. So now we have this funny looking sequence down here. Pause it and try to do the same 4 things. I'll stop here for a second while you do that. And then I'll pick back up just like right now. So it doesn't really look like an arithmetic sequence, but when you do this, A is equal to, D is equal to, the common difference is equal to ln of 6 minus ln of 3. We remember that our logarithmic rules just mean we can divide in here. So this becomes ln of 6 divided by 3 is 2, which is the same thing as ln of 12 minus ln of 6. I'm just showing you guys here. We found the common difference already. It's ln of 2. I'm showing you that using any of the other differences, you still get ln of 2. So you have 12 divided by 6. You still get ln of 2. Even if I wanted to do that whole jumping steps thing here, I could have ln of 24 minus ln of 3 over 1, 2, 3 steps there. So over 3, this becomes, I know how to do this, so I'm going to call it 1/3 instead of divide by 3. 24 divided by 3 gives me 8. I bring in that 1/3 power. This becomes ln of 8 to the 1/3 power, which is just ln of 2. Again, you don't have to do those multiple ways of doing it. I was just trying to show you all of the fancy mathematical arithmetic that we can do. Mathematical acrobatics, not arithmetic there. So our common difference, ln of 2, however you want to find it. B, ninth term. I'm not going to do the ninth term until I do part D. So real deal. Here's the order in which I would do it. I would do A, C, D, B. Save the B for when I have the explicit definition. So for part C, I've got my A sub 1 is equal to ln of 3. A sub n is going to be equal to... I gotta fix something here in a minute. So A sub n is going to be equal to the ln of 3 plus... That's the explicit definition. Sorry, I got distracted. I was supposed to put a sub 1 up here. That was just messy of me. So A sub 1 is equal to ln of 3. A sub n is going to be A sub n minus 1. Added onto it is the common difference of that ln of 2. I was overcomplicating the recursive rule. I always think the recursive rule is easier to write out. Because for part D, to find the explicit rule, you actually have to think. And here's where I get a little bit crossed. I have the initial term, ln of 3, plus the common difference, ln of 2, times the quantity of n minus 1. I don't know if we want to clean this one up. Yeah, no, okay, fine. This becomes ln of 3 plus n ln of 2 minus ln of 2. Did I get that right? Yeah. So now I can change this into ln of 3 plus ln of 2 to the nth minus ln of 2. This becomes ln of 3 times 2 to the nth minus ln of 2, which becomes ln of 3 ln, no, this becomes ln of 3 times 2 to the nth all over 2. Okay, yeah, that was way more complicated than I thought it was going to be at the beginning. I would leave it here in this case. That was really, that was actually kind of fun. So I guess now I have to go back and find A sub 9, which would be equal to, let's go to the easy one, ln of 3 plus ln of 2 times the quantity of 9 minus 1. Okay, so here we would have 8, right? So 8 ln of 2, 8 ln of 2 would be ln of 3 plus ln of 2 to the 8th. Again, that 8 is just a factor, so I bring it up as my exponent here. Man, this is going to be messer. 2 to the 8th times 3, 768. ln of 768. And yeah, there we go. Work for the first one. Work for the second one. Yeah. Oh, hey, cool. Whoa, look at that. Look at what I had here. That was simplified a lot better. So that ln of 2 to the nth divided by ln of 2 just becomes 2 to the n minus 1. That's a lot cleaner than what I had, but yeah, whatever. Next thing we have is geometric sequence. I've heard a lot of talk about geometric sequences on the news recently. A sequence, a sub n, is a geometric sequence if it can be written in the form a times a. Next term, a times r. Next term, a times r squared. Next term, blah, 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 a times r to the n minus 1. I will point out right here, there's your explicit definition for geometric sequences. A sub n is equal to a times r to the n minus 1. That's important to note. For some non-zero constant r, the number r is called the common ratio. Each term in a geometric sequence can be obtained recursively from its preceding term by multiplying by r. A sub n is equal to a sub n minus 1 times r for all n greater than or equal to 2. Okay, well, here we go. For the geometric sequence, 1, negative 3, 9, negative 27. Find the common ratio. So to find the common ratio, what we have to do, instead of finding the common difference, it's a common ratio, so you're just going to divide two terms here. So you could actually have r is equal to, well, negative 3 divided by 1, 9 divided by negative 3. Let's just take the fun one. 9 divided by negative 3 is going to give me negative 3. We could also, if we wanted to be fancy about this, we could take the ratio of negative 27 divided by 1 and take the cube root, because we've actually repeatedly multiplied on here. So I could do negative 27 divided by 1, cube rooted, I get cube root of negative 27 is negative 3. Doesn't matter how you do it, as long as you find the common ratio here. Part B, 10th term. Okay, so 10th term, 1, 2, 3. I'm taking out my calculator. Are you kidding me? I'm not going to multiply like that on here. Negative 27 times negative 3. So that would be the 5th term, 6th term, 7th term, 8th term, 9th term, 10th term. Whoa, that's quite large. Okay, I had to cheat there and make sure that I wasn't given the wrong number here. So let's just call this, again, a sub whatever. So a sub 10 is going to be equal to negative 19,683. Yeah, cool. C, recursive rule. Okay, recursive rules are actually really easy. You say a sub 1 is equal to the first term. A sub n is going to be equal to the previous term, a sub n minus 1, times the common ratio. Common ratio was negative 3. I like to write this more in the terms of negative 3 times a sub n minus 1. It just looks prettier. All right, so there's your recursive definition. Oh, for n greater than or equal to 2. All right. For part D, we've actually got repeated multiplication this time around. So for repeated multiplication, what we have to do here is take the first term and multiply by your common ratio to the power of however many times you've multiplied it on. So here, for the second term, we would be multiplying by once. Third term, we'd be multiplying twice. So here is where we get that n minus 1. Honestly, I would keep this as negative 3 to the n minus 1. And then you're done. All right, cool. Do this one. I'll come through and I'll try to explain it real quick. All right, cool. That was enough time. A, your common ratio is going to be equal to, let's go for the easy one, 1/2 divided by 1, which is going to be equal to 1/2. B, going to save that for when I have letter D done. But part C, I've got a sub 1 is equal to 1. A sub n is going to be the previous term times 1/2. Or a sub n minus 1 over 2 would be a fun way to write it. D, a sub n is going to be equal to common ratio times, the first term times the common ratio to the n minus 1, which in this case would be 1/2 to the n minus 1. So looking back here, if I'm trying to find the a sub 10, I would have 1/2 to the 10 minus 1. 10 minus 1, I believe, is 9, right? 2 to the 9th is 512. So this becomes 1/512. Done. Backside. Second problem. And second and fifth term of a geometric sequence are -6, 48, respectively. Find the first term, common ratio, and an explicit rule for the nth term. Okay, this is a little bit difficult to do. Basically, all we're told here is a sub 2 is equal to -6. A sub 5 is equal to 48. We want to know what a sub 1 is. We want to know what r is. We want to write an explicit rule for the nth term. Okay, so we got to find the common ratio. Well, it looks like to me to get from 2 to 5, I would have to go three steps, right? 2 to 3, 3 to 4, 4 to 5. Yeah, I'd have to do 3 steps. So I would have had to multiply 3 times to get from -6 up to 48. So I look here to find my common ratio, just thinking backward a little bit here. I would have my common ratio of 48 over -6, but that's not the common ratio here. This is 3 times of my common ratio. So I'd have to cube root. I'd have r is equal to the cube root of -8, which is -2. All right? No, there's actually an easier way to think of this one. Whew, man. I happen to know that a sub n, just going from my my definition of a geometric sequence, my a sub n is going to be a sub 1 r to the n minus 1, right? So looking at this, I know that I'm going to have -6 is going to be equal to a1 r to the 6 minus 1. Okay, that just becomes a1 r to the 5th. Down here, 2, 2, 2, 2, right there. Okay, maybe 1. Okay. Ignore that I just made all of those grievous arithmetic mistakes. A sub n is a1 r to the n minus 1. This would now be a1 r to the 2 minus 1. a1 r to the first, just a1 r. Down here, I'm going to have a1 r to the 5 minus 1, which would be a1 r to the 4th. Now, if I wanted to divide these two, I could have a sub 5 divided by a sub 2, which is equal to 48 divided by -6, which is going to be equal to a1 r to the 4th divided by a1 r. Okay, cool. That becomes a little bit quicker, r cubed. And I can get this equation from that. Yeah. So either way, if you could figure out how I was talking about it when I did it up here, or if you like the equation tends to be a little bit easier. Either way we look at it, we now have r is equal to -2. Bueno. Now we just have to find a1. Well, a1, again, a sub n is a1 r to the n minus 1. Let's just choose the easiest one that we have. -6 is equal to a1 times my common ratio of -2. Okay, divide by -2. That means a1 is equal to 3. Okay, very cool. Now, if only I had a way to plug stuff in. A sub n is equal to a1, 3 times r, -2 to the n minus 1. Yeah, cool. That's fun. Sorry about all those hiccups that I had in the middle there. And you can see I actually have the work here, so I should probably look at my work to remind myself I do this. You can graph a sequence either using parametric mode or sequence mode on your calculator, on your graphing calculators. When you do this, make sure you use dot mode. You can look at how to graph sequences in your book if you want. It's on page 438. I'm not going to do that. Limit. Let L be a real number. The sequence a sub n has limit L as n approaches infinity if, given any positive number epsilon, there is a positive number m such that for all n greater than m, we have the magnitude of a sub n minus L is less than epsilon. We write the limit as n approaches infinity of a sub n equals L and say the sequence converges to L. Sequences that do not have limits diverge. A lot of stuff on there. Don't worry about a lot of the technical stuff, like the epsilon, not really that needed to understand this stuff. The important stuff is this word and this word. If the limit exists, the sequence converges to L. If the sequence does not have a limit, it diverges. We've used those words before. Properties of limits. If L and M are real numbers and the limit as n approaches infinity of a sub n is equal to L, and limit as n approaches infinity of b sub n is equal to m, then sum rule, difference rule, product rule, constant multiple rule, quotient rule. They're all the limit rules that we had in chapter 2. Pause, write that down if you need to. Moving on. Determine whether the sequence converges or diverges. If it converges, find its limit. A sub n is equal to 2n minus 1 over n. So all of that really tricky stuff on the 2 slides ago. All that means is we're finding the limit as n approaches infinity. When we're talking about limit of sequence, it's always n approaches infinity of a sub n, which is equal to the limit as n approaches infinity of 2n minus 1 over n. Now I see we've got infinity over infinity. We know L'Hopital's rule is not that hard, but this came before the L'Hopital's rule section. You're allowed to use L'Hopital's rule, but since it came before that section, I'm just going to show you guys how you can do it without L'Hopital's rule. Split it up into the 2 different fractions. N's cross off over here. That becomes 0. This becomes 2. So a sub n converges to 2. Done. Its limit is 2. It converges to 2. All right. Stuff. I guess that could be a factorial as well. Or I got excited. One of those. Yeah, you guys love sandwich theorem, don't you? Sandwich theorem for sequences. If limit as n approaches infinity of a sub n is equal to the limit as n approaches infinity of c sub n is equal to L, and there's an integer n for which a sub n is less than or equal to b sub n, less than or equal to c sub n, for all n greater than n, then the limit as n approaches infinity of b sub n is equal to L. Absolute value theorem is if you're dealing with an alternating sequence, you take the absolute value. If the limit as n approaches infinity of the absolute value of a sub n is equal to 0, then the limit as n approaches infinity of a sub n is equal to 0. Otherwise, the sequence diverges. Determine whether the sequence converges or diverges. If it converges, find its limit. Okay, cool. All right. So in order to find this, ooh, man, when I look at this, I see that writing this out, a sub 1 would actually be negative 1. A sub 2, when I raise the positive to the second power, that becomes 1/2. Then I've got negative 1/3. Then I've got 1/4, negative 1/5. I'm specifically trying to get you guys to acknowledge that this is an alternating series. Basically, whenever you see that negativity to an nth power, we want to use the absolute value, what was it called? The absolute value theorem. That's what I was going to say it was called, but I wasn't sure if we just invented another word in there. So, to find the limit as n approaches infinity of this, we're going to find the limit of the absolute value of a sub n. If it equals 0, the sequence converges to 0. If it equals anything else, it diverges. So looking here, this would be the limit as n approach infinity of the absolute value of -1 to the nth power over n. It allows me my first opportunity to give you guys a heads up here. If you take the absolute value of -1 to the nth, well, -1 to the nth is either 1 or -1. Take the absolute value, negativity now no longer matters. This becomes limit as n approaches infinity of 1 over n. Infinity in the denominator, this ends up being 0. And I can't do an exclamation point on that because 0 factorial is equal to 1. All right, cool. Boom, 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 boom. Yeah, wow, it looks like I used sandwich theorem up here. I kind of like using the absolute value theorem a little bit better. It was cooler. Homework. It's listed on your page as well. So don't forget to smash that like button.